Hello friends. So today, one second, we are going to solve two questions, and these two questions are from our electric potential and somewhat related to electrostatic also. So the first question is given in the figure cross section a flat metal box in which there are two flat plates 1 and 2 each of area A. The potential of the box is chosen to be 0. The various distances separating the plates from each other from the top and the bottom box are labeled as R, S and T in the figure are to be assumed small compared to the width and the length of the plates. So it will be good approximation to neglect the edge fields in estimating the charges on the plates. In this approximation, work out the capacitance coefficient C11, C22, C12 and C21 and check that C12 is equal to C21. So in this case, we are given the basic figure, and let me draw it. So we are given that we are having a kind of box. Suppose this is a kind of box, and inside it there are two plates. Okay. Suppose this is plate number 1 and this is plate number 2. And along with it, respective distances are given as R, S and T. Okay. So let us suppose this distance is given as our R, this distance is given as our S, and finally this distance is given as our T. And so this is basic figure given to us. Okay. So we are going to start it because from the figure we can easily see that this is nothing but a kind of a parallel plate capacitor. Okay, a combination of parallel plate capacitor. Okay. So we are going to start from the bottom part. Okay. So we can say that each gap behaves like a parallel plate capacitor. We can see that our each gap behaves like a parallel plate capacitor. And let us start from the bottom side. So first is up from the bottom side, and that will be result in a parallel plate capacitor which we can represent as plate 1 and the bottom. Okay, and so we can write this as our plate number 1, and B stands for the bottom. And the standard formula we already know is there epsilon naught A and the distance between the plates. Okay. And along with it, we can also find out what will be the respective potential. Okay. And from here, we can also say the potential difference between the first plate and the bottom will be equal to potential on the first plate and potential at the bottom. And potential at the first plate is, let us suppose, given as phi1, and the potential at the second plate is, let us suppose, given as phi2. So this will be phi1 minus, and the enclosed is given as 0 potential. So this will be phi1 minus 0. So we can write this is equal to our phi1. Then we come to a middle portion. middle it will be consisting of plate 1 and plate 2. Okay. Once again, area is same, and only thing that is going to vary is the distance, which is given as S. And from here also we can write that the potential difference between plate number 1 and plate number 2 will be equal to potential at plate number 1 minus potential at plate number 2. And then we come to our top part, and top will be our plate number 2, and top, let us suppose, is denoted as T. Okay. So this is our bottom B and this is our top T, and this can be written as our epsilon naught A, and the distance is given as between the plates is given as T. And from here we can also find out the potential difference, the plate number 2 and the top, that will be equal to our potential at plate number 2, and the enclosed is given as having a 0 potential, so this will be phi 2 minus 0, giving us our potential. Okay. And we know the basic thing, that the total charge on each plate is sum of the contribution from the adjacent capacitors. Okay, so this is an important conclusion. Okay, so we know the total charge on each plate is the sum of contribution from adjacent capacitors, is the sum of contributions from adjacent capacitors. So this is the basic statement, or we can say result, which we are very well aware of. Okay. And so in order to find out this particular statement, we are in order to find out the equations based on this particular statement, we are going to solve this using two experiments. Okay, or we can say we are going to consider various values of potential. That is going to help us to define this, that how our this charge, suppose on plate 1, that is Q1, is dependent upon our phi 1 as well as phi 2. Okay. So let us say this for our part A, and in order to part A, we are going to assume that our phi 1, that potential on plate 1 is not equal to 0, but potential on plate 2 is equal to 0. Therefore, based on this, we can write the equation for the voltages. And the voltages, we can write that the bottom gap and bottom gap is nothing but our V, which is equal to our phi 1 minus 0, which gives us our phi 1. And then we come to our middle gap, then this V will be equal to, basically that is our phi 1 minus phi 2, but we have taken that our phi 2 is equal to 0, so this will be also given us our phi 1. Okay. And then we come to our top gap, and top gap, we know that that equation is our phi 2 minus 0, and we know that phi 2 is 0, so this also gives us 0. Okay. And we know that the charge, basic equation between a relationship between the charge and capacitance, we know that our charge, that's our Q, it is given as our capacitance multiplied by the potential. Okay. Therefore, we can write this as our on plate 1 from bottom gap. So we can say on plate 1 from bottom gap. And that we can easily write that, let us suppose that charge is our Q, and that we are going to find out on plate 1, and the bottom gap is given as A. Okay. And this we are solving for our part A, so we are going to put a here. Okay. And this will be equal to our capacitance between this plate 1 and bottom, okay, multiply by the potential on it. And we already know all these values, so this we get as epsilon naught A R multiplied by phi 1. Okay. Now we come to its second part, that is on plate 1 from middle gap. On plate 1 from middle gap. Same equation we are going to write, but the variables are going to change. So plate still is 1, middle gap is given as our S, and we are dealing with part A. Okay. And that will be equal to capacitance between the plate 1 and plate 2 multiplied by the, we can say, the voltage. Okay. And the voltage we know is our phi 1 minus 0, which we have already calculated. Okay. So we can write this will be equal to our phi 1 minus 0. So we get this as our epsilon naught A divided by S and multiplied by our phi 1. So it means the total charge on plate total charge on plate 1 will be the combination of these two. Therefore, we can write from here that total charge on plate 1, and once again we can write this as charge on plate 1 because of part A. This will be equal to our Q1 RA plus Q1 SA, which gives us, we can take phi 1 as common, okay, and this variable also common, so this comes as epsilon naught A, and this will be 1 upon R plus 1 upon S times phi 1. So we got the relationship for our charge on plate 1. Now we come to same experiment. Now we shift to our plate 2. Now we know that plate 2 is at 0 and is only connected by the middle gap. Okay. So we know that our plate 2 is at 0, okay, because from here we can clearly see that our phi 2 is equal to 0. Okay. Therefore, we can say the plate 2 is at 0 and only connected via middle gap. It means our charge on plate 2, charge on plate 2. Okay. And once again we can write this as our middle gap is going to result an opposite charge on the plate 2. So we can say our middle gap gives opposite charge on plate 2. And it is quite obvious, because if one of the plate is having a positive charge, then the other plate of the parallel plate capacitor is bound to have a negative charge. Therefore, we can write that charge on plate 2, because of the distance between the plate is s, and for part A will be equal to minus of the charge on plate 1, because of the distance is s and experiment is our part is our A. So this gives us negative epsilon naught A s times our phi 1. And top gap, they are having the same voltage, 0 and 0, so there is no extra charge on it. So you can say the top gap has no voltage, because it is 0 minus 0, because we know that the top gap is at 0 minus 0. Okay, so therefore we can say top gap has no voltage. Therefore, from here we can write no extra charge. No extra charge. Therefore, total charge on plate 2 charge on plate 2, let us call this as our Q2, because of our part A will be equal to minus of our epsilon naught A s times our phi 1. Later on we can just you can say also justify the answer. Okay, we are going to solve it further, and we are going to get the same results. Okay, now we come to our part B. And in part B, we are going to assume that our phi 1 is equal to 0, but our phi 2 is not equal to 0, just reverse of our part A. Now we come to our voltages. Once again, same process. We come to our voltages, and voltage we start from the bottom gap, and for bottom gap we know that the voltage is over phi 1 minus 0. Okay. This is phi 1 minus the bottom is at a 0 potential, and phi 1 in this particular case is also 0, so this comes as our 0. Now we come to a middle gap, and middle gap is nothing but our phi 1 minus phi 2. Okay, so phi 1 is our phi 1 minus phi 2. Phi 1 is our 0, so this comes as minus of our phi 2. And then we come to our top gap, and this gives us that V will be equal to our phi 2 minus 0, which is nothing but our phi 2. Now based on these voltages, we are going to find out the various charges that are available on plate 1 and plate 2 respectively because of the gap, and then we are going to add them. So we can say charges, and first one is a charge on plate 1 from the bottom gap. Yeah. So we have charges, and the first we are going to write on plate 1 from the bottom gap. On plate 1 from bottom gap, and this is for our plate 1, distance is r and part is our B, and obviously there is no voltage, therefore this is equal to 0 because the voltage is 0. Because of voltage, there is no charge. Now similarly on plate 1 from the middle gap. On plate 1 from middle gap, and we can write this as our Q1, plate 1, middle gap is S and part is B, and once again this is our C1, 2, and the difference in the potential, that is 0 minus our phi 2. So this gives us that our charge on plate 1 because of middle gap, part B, is equal to negative of our this. Okay. So we get this as minus epsilon A and times our phi 2. And now we come to our plate 2. On plate 2, and so first of all for plate 2 we are going to solve it for our middle gap. So we can say from middle gap, we know it will be just opposite of our plate 1. Opposite of plate 1 in that gap. Therefore, we can say that our charge on plate 2 because of gap S and part B will be equal to negative of charge on plate 1 because of same gap S and part B. So this comes as negative of negative. So this will be our epsilon naught S times our phi 2. And then is our from top gap. And we can write this as our Q2, T is the distance between the top and the second plate and the top. For part B will be equal to the capacitance between the two and the potential difference. Okay, so this comes as epsilon A T times our phi 2. Therefore, total charge on plate 2 total charge on plate 2, and that will be equal to our Q2 part B, and this we can write will be equal to our Q2 distance S part B plus Q2 distance T and part B. Therefore, we get that Q2B will be equal to epsilon A S plus 1 upon T times our phi 2. So we were able to find out the respective charges on this. Okay. But in this case, in part A and part B, we assumed that one of the potential is equal to 0. So what is going to happen if both phi 1 and phi 2 are non-zero? Okay. In that case, there will be superposition. So you can say that our phi 1 is not equal to 0 and phi 2 is also not equal to 0, because we know that our electrostatics is basically linear. Okay, it's a linear, so it means the effect of both the voltages together is sum of the effects of each taken separately. Okay. It means if the total effect is our suppose V1 plus V2, okay, then we can solve for V1 separately and add it to V2 separately. So the answer will be same. Okay, this means electrostatic is linear. The effect of both voltage taken together is sum of the effects of each voltage taken separately. Okay. So basically we can say we are going to use superposition. And so let us consider for our plate T1. So plate 1 we can write that our contribution from potential phi 1 contribution from phi 1 alone, and we have just calculated it is charge on our Q1, that is because of part A, is epsilon naught A 1 upon R plus 1 upon S times phi 1. Similarly, we can write contribution from phi 2 alone, which is our Q1B, and that is also equal to our minus epsilon naught A upon S times phi 2. Okay. Now we can just add them. So we can say our charge on our plate 1, that is Q1, will be because of our plate 1 because of A and plate 1 because of our B. So we can just algebraically add them. So we get epsilon naught A, and this is our 1 upon R plus 1 upon S times our phi 1, and this comes a minus epsilon naught A S times our phi 2. Same thing we did for our plate 1, and now we are going to do same for our plate 2. For our plate 2. And first comes to contribution from our phi 1 alone. Contribution from phi 1 alone, that is our Q2A, that is our minus epsilon naught AS times our phi 1, and then it is contribution from our phi 2 alone, and that is our Q2B, and it is epsilon naught A 1 upon S plus 1 upon T times our phi 2. So it means total, that is our Q2 will be equal to Q2 because of A plus Q2 because of our B, and we can simply substitute the values. We get this epsilon naught A upon S times phi 1 plus epsilon naught A 1 upon S plus 1 upon T times phi 2. So this gives a relationship, or we can say we got the charge on our plate 1 as well as plate 2, and this entire calculation was based on only one statement which we wrote here. Okay, this is a standard statement with respect to, it states that the total charge on each plate is the sum of the contribution from the adjacent capacitances. So this is an important, you can say, statement with respect to our capacitance. Now we can easily write our charge equations with respect to capacitances also, okay, or sometimes these are also called as a capacitance coefficients. And so we can write that our charge on our Q1 on plate 1 will be equal to, because of our C11 phi 1 plus C12 phi 2. Similarly, charge on a plate 2 will be our of C2 phi 1 plus C22 phi 2. This is also the direct relationship of our statement, because we know that a charge is nothing but a product of capacitance and the potential. Okay, so this is between the gap of our phi 1, and this is because of our phi 2. Similarly for our this charge on Q2 also. Okay. And so we already know the, you can say, coefficient of C11. Okay, so if we make a comparison with this equation, this equation. Okay, let's say this equation is 1 and this equation is over 2. This equation is over 3 and this equation is over 4. So we are going to make a comparison between 1 and 3, 2 and 4. Okay. So we can say from equations 1, 3 and 2, 4. We are going to get that our C11 will be equal to epsilon naught A 1 upon R plus 1 upon S, and we are going to get this our C12 is equal to minus epsilon naught A upon S. And similarly, based on our this 2 and 4, we can write that our C21 is equal to minus epsilon naught A upon S, and C22 is equal to epsilon naught A 1 upon S plus 1 upon T. So we were able to get the respective our the coefficients, and one of the things we got the values which we were required, all the capacitances, and in this particular case it was also asked to check whether C12 is equal to C21. So from here we can easily see that our C12 is equal to our C21. So these are the values of our the capacitances. Okay. And we have to remember this is a beautiful example of how this equation or the question can be sometimes misleading. Okay. So we are given that we have a box which is having zero potential, and between them there are two plates. See, plate number 1 and plate number 2, and the distance between this is given as R, this plate is given as S, and this plate is given as T. And we are supposed to find out what will be the respective capacitances C11, C22, C12 and C21. Okay. And we assume that this is potential on 1, this is potential on 2, this is our bottom and this is our top, and the entire box is at zero potential, so this bottom will be at 0 and the top will be also equal to 0. And in this case we use the concept that the charge on the plate, suppose plate 1 will be because of the charge stored because of itself and because of the other plate also. Okay, so the charge on the plate 1 will be the effect of both charges, itself as well as because of plate 2, which was our main statement. Okay, like this. So charge on 1 will be because of itself and the other part also. Okay. And here also we wrote this statement, and this statement plays an important part here also. So we wrote that the total charge on each plate is sum of the contribution from the adjacent plate. So this is an important contribution or statement, and this defines our particular solution. Okay. Next question. Okay, so it states that two metal spheres A and B forming a left pair are connected by a conducting wire, and the total charge on this pair is 0. Two metal spheres C and D forming the right pair, two oppositely charged conducting spheres, are brought near A and B and then connected by a conducting wire. Basically we have to find out how the charge is going to behave in this particular case. Okay, I forgot to add that part, but the question is clearly mentioned with respect to the figures. So initially we are having only two charge sphere A and B, okay, and it is given that they are having a net, suppose this A is having a charge of our QA and B is having a charge of our QB, and their summation is equal to 0, that is given to us. In part B, in figure B rather, we bring two charge spheres C and D, and both are oppositely charged. From figure we can clearly see that our C is our positively charged, okay, and this is our negatively charged, and they are brought together with A and B, near A and B, not connected. Okay, then after some time, both C and D are connected with the wire, okay, by conducting wire, and so we have to see how this everything is going to behave. Okay. So this is a basic question, and this entire discussion, or we can say the solution, is based on the charge conservation. Okay. From the looks of it, looks that it might be very difficult, but if you go step by step, you can understand that the charge conservation plays very important part. Okay. Obviously, whenever we are going to connect or bring this A and C and B and D, the charge redistribution is bound to happen. Okay, that is going to take place, but there will be no loss of charge. We have to remember this. Okay. So let us go step by step. First, only A and B are connected. Okay. So we are having as stage 1, and stage 1 is that only A and B are connected. Okay. And it is given in the question that the total charge on A is equal to 0. A and B total charge is given as 0. Okay. So we are mentioned in the question, we are given that total charge on the pair is 0. Therefore, if you assume that our A is having a charge of our QA and B is having a charge of QB, therefore we can write that QA plus QB is equal to 0. And C and D are still not connected, it is somewhere else, but they are oppositely charged. So we are also given that C and D are oppositely charged. They are oppositely charged, and therefore let us assume that C, from the figure we can easily see that our C is our plus Q and D is our minus Q. Okay, so we can say C is our Q and D is our minus Q, and for the sake of convenience, let us write this as our QC plus QD. Obviously this summation will be equal to 0. Okay. Now we come to our stage 2. Okay. Stage 2, we bring C and D close to A and B. We have stage this 2. Okay. C and D are brought near A and B. Please remember, stage B, C and D are still not connected. Okay, they are connected in last stage, that is stage 3. We have to remember this part. Okay. Obviously, because the charge redistribution is bound to going to take place, but the total charge respectively, because of the conservation, will be still equal to 0. Okay. We are not aware what is the value of QA, we are not aware what is value of QB, we are not aware what is value of QC, we are not aware what is value of QD, but we are given that QA plus QB is equal to 0 and QC plus QD is equal to 0. Therefore, if before and after we say that before connection, before bringing them close, the summation is entire equal to 0. Okay, so if we add these two terms, we get the QA plus QB, QC plus QD is equal to 0. So it means after they are brought together nearby, something like this, the entire summation will be still equal to 0. So this condition is bound to hold. Okay, that is nothing because of the charge conservation. Therefore, we can say that the total charge on A and A plus B, total charge on A plus B is still equal to 0. Similarly, we can say that the total charge on C plus D is still equal to 0, okay, because of the charge conservation. Okay. And so we can say, because we get this impression that as they are going to, both are coming together, the charge redistribution is bound to happen. Okay, some charge will be going from A to B, A to C, and sometime to C to A, then B to D or D to A, and A and B are also connected. So there will be a charge redistribution among all these 4 spheres, but their summation will be still equal to 0. This thing we have to remember because of the charge conservation. Now we come to our stage 3. And stage 3, we know that now the C and D are connected. Okay. Now, as C and D are connected, so the charges will start to flow between C and D also now. Therefore, we can say that charges are now allowed to flow between C and D. Between C and D. Okay. But it doesn't mean that the charge is going to come from somewhere else. The charge is already there. It is so, once again, because of the conservation, the summation of charges will be still equal to 0. So it means the charges on C and D will be still equal to 0. Okay. So we can say from conservation, our QC plus QD will be still equal to 0. Okay. And we can also, you can say, but that doesn't matter, okay, because simply we can say because of the conservation, we can say that the summation of the charges will be still equal to 0. Okay. Their individual values can vary, but their summation will be always equal to 0. The QC might increase, QD will be decreasing in same proportion that the summation is equal to 0. And we are not aware whether which is changing, which is increasing and which is decreasing. Okay, we are only aware that the summation is equal to 0. Okay, that is bound to happen. Now, so ultimately, from this entire discussion, everything comes to only 2 equations. Okay. We get the result that our QA plus QB will be equal to 0 and our QC plus QD is equal to 0. Okay, so from this entire discussion, we get these 2 important results, and this is according to our conservation. Okay. And as soon as our C and D is connected, okay, with the wire, there will be a certain change, and that change we know is that our potential at C should be equal to potential at D. This is the only change that is going to happen. A and B are at the same potential because they are already connected. C and D will be coming to a same potential when they are interconnected with the wire. Okay, so we have to remember this thing. So we can say that when C and D are connected, one second. So when C and D are connected, only one thing is going to change, that is our this potential at C will be equal to potential at D. Okay. So when C and D are connected, potential at C will be equal to potential at D. Okay. Or we can say they are at equipotential. They are at equipotential. Okay. And because of this, the charge distribution is going to change from QC to QD to some other value, but the summation will be still equal to 0. And we already know for our potential equation, we know that in general equation, we can write that potential V is equal to K Q upon R. This is a general equation, and we know that value of K is 1 upon 4 pi epsilon naught. And so, and this is true for if we are having one charge, and if we are having a multiple charge. So this is true for our one charge. Now if we are having multiple charges, we can write, we are going to use the basic superposition, that is sum of their individual potential. Sum of individual potential. So it means if you are having two charges, one is Q1, other one is our Q2, okay, and they are respectively at a distances R1 and R2, okay, from point P, from a point P. Therefore, we can say that potential at point P will be equal to potential at because of charge 1 and potential because of our charge 2. So we can write this as K Q1 upon R1 plus K Q2 upon R2. This is our basic, you can say, basic our potential. And this we can extend to n number of charges. So we can say our from Q1, Q2 up till Qn, and respectively the distance is our R1, R2 and Rn. Same at point P, we can write that potential at point P will be equal to our summation J1 to n K Q of J upon R of J. This is our basic. Now we come to our original question, that is our charges A and B, and in this case we are going to use these particular relationships. Okay. And so we can say potential on the conductors, these are basically the conductors, spheres, due to conductor charges. Okay. You can say potential on conductors due to conductor charges. And we know that we are going to consider these irrespective of the conductor. We are going to treat them as now a point charges. We know that our sphere A, it carries a charge of our QA. So from here we can write potential at any point on B. Potential at any point on B due to A alone. We can write this as our equation, that potential at B due to A alone will be equal to, let us suppose we have this as our alpha. Okay, alpha we can just define later on, and alpha is equal to B A, and this is charge of our A. And this alpha is nothing but a constant, and that constant is equal to ratio of the our K as well as their distance. Okay. So we can say this alpha BA is equal to over K and the distance between the two, that is RBA. Okay. And now we come to our, with all the spheres charged, the potential at A will be equal to the sum of contribution from the each, which is a basic principle. Okay, we just found out that is it is a summation of the individual voltage potential. Okay, like for two charges we said if the potential at point P is Vp, then it is potential to charge Q1, potential due to charge Q2. And therefore we can write that with all spheres charged, potential on A Okay. And for that we can write the equation potential on A, that is VA, will be potential of A because of its self charge plus potential on A because of the charge on sphere B plus potential on A because of charge on C plus potential on A because of charge on D. Okay. So indirectly we are saying that our, now we can easily replace these individual potentials with their respective equations. Okay, like here we said that the potential on B because of A, we wrote a certain general equation. Similarly, we can write this for our VA. Okay. Therefore, we can write that our VAA, that is our VA, will be equal to our alpha AA times charge QA plus alpha AB and charge on B, that is our QB, plus alpha AC and charge on C plus alpha AD, and this is charge on our sphere D. So this is nothing but respective individual voltages because of their respective charges, because we are having total 4 spheres. So we found out of VA their self potential because of charge B, QC and QD. Similarly, we can write for all the 4 charges. So we can say similarly our VB will be equal to alpha BA times QA plus alpha BB times QB plus alpha BC times QC plus alpha BD times DD. And this is our B. Then we come to a C. Similarly, alpha CA times QA plus alpha CB times QB plus alpha CC times QC plus alpha CD times QD. And finally, we get to our potential at D will be equal to alpha dA times QA plus alpha dB times QB plus alpha dC times QC plus alpha dd times QD. Okay. And please remember, this is entirely based on only one equation, that is potential at any point will be, suppose there are two charges, then the potential due to first charge plus potential due to second charge. And if there are n number of charges, this can be extended into n number of equations. Okay, so same we wrote it. And here this alpha and this coefficient alpha, it is nothing but a ratio of their ratio of the k and the distance between the two. Okay. Now to just simplify it, because we need to solve anything, we are just going to write the general expression. So the alpha is equal to our k is 1 upon 4 pi epsilon naught, and the ratio of our distance. So this is our alpha, and respectively we divide it into our AB, BA and so on. Okay. Now we know, because of the wire, the potential at A will be equal to potential at B. Okay, because A and B are connected in wire. We can also call this as our wire condition. And say, because of the wire connection, we are going to call this as a wire condition. Okay. And for the wire condition, we have two pairs. We have our AB pair, and they are connected with the wire. So obviously we know after some time they are going to have the same potential, that is our VA is equal to our VB. Okay. Now we are going to equate our VA is equal to our VB. Let us call this our equation number 1, 2, 3 and 4. So we can say from 1 and 2, therefore from 1 and 2 we can write that our alpha AA QA plus alpha AB QB plus alpha AC QC plus alpha AD QD will be equal to, and this will be equal to our alpha BA, and this will be equal to alpha BA QA plus alpha BB QB plus alpha BC QC plus alpha BD and QD. And now we can just segregate the terms. This is our QA and this is also QA. Okay. So we can take this common, so we get this as alpha AA minus alpha BA times QA plus alpha AB minus alpha BB times QB, and this is a plus alpha AC minus alpha BC times QC plus alpha AD minus alpha BD times QD is equal to 0. And similarly we can do for our CD pair. So we can say similarly for our CD pair we can use from equation 3 and 4. Okay. We are going to get almost identical, but the variables will be different. We are going to alpha CA minus alpha DA times QA plus alpha CB minus alpha DB QB plus alpha CC minus alpha dc times qc plus alpha cd minus alpha dd times qd is equal to 0. Yeah. Or in shorter terms, in both the cases, here also we can write that the summation of our alpha multiplied by the charge is equal to 0. Okay, variables we can add. Similarly, from this we can also write that the summation of our alpha times their charge is equal to 0. So these were our respective how the charge redistribution is going to take place. Okay. If the values are given to us, we can solve all these two equations, or previously there were 4 equations. But in this particular question, we have to remember that everything is dependent upon charge conservation, and secondly, whenever we connect two charged bodies, they should be, after some time, because of the transfer or redistribution of charges, they will be coming to same potential. Okay, so this was the basics. So today we discussed only 2 questions because they were quite lengthy to solve. And in the first part, we discussed the effect of capacitance. Okay, how the capacitance is going to change when there are certain conditions associated with it. Okay, and in that case also, we have to remember that capacitance charge is dependent upon the charge on the other plate also. Okay, so the charge on plate 1 will be dependent upon the charge on plate 2 and vice versa. So this completes today's question for 2. Thank you.